They will be talking about the efficiency of Gauss Seidel and convergence of iterative methods.
So I'm going to start our talk off by talking about solving systems of linear equations. Usually they're represented in this form, which is called matrix equation form, where A is the coefficient matrix, X is the unknown matrix or the variable matrix, and B is the solution matrix. But they can also be represented in the equivalent forms shown here, the equation form and Alexander form. Now, by definition, a system of linear equations is a set of equations that you're trying to find a common solution for, or show that a common solution does not exist. Now, there are several ways, or two main ways actually, two main categories of finding a solution for these systems, and that's by direct methods or by iterative methods. Now, direct methods involve manipulating the matrix or equations directly by using row operations, swapping rows, multiplying them by scalars, or adding them together to basically get them in a form that you can interpret as a solution, or just that you can get a solution from. And these methods usually involve, or always involve, a finite amount of steps, and they find an exact solution, and the number of steps is always dependent on the size of the matrix or the amount of unknowns you have. And examples of direct methods involve Gauss-Jordan, Cramer's rule, LU decomposition, Gaussian elimination, among others. On the other hand, iterative methods involve an approximation and an initial guess, and using the approximation, the initial guess is successively refined to get closer and closer to converge upon that value, and once it gets within a certain amount of error to that solution, you just call it the solution, and that's your answer. But sometimes it could also just diverge completely, which we'll also talk about later. And examples of iterative solutions include Gauss-Jacobi, Gauss Seidel, successive overlappation, and conjugate gradient, and others. The main topic of this presentation will be over Gauss-Jacobi and Gauss Seidel.
So the main difference between Gauss-Jacobi and Gauss Seidel is that Gauss Seidel is more efficient due to using calculations from the current iteration. The number of computations required for sufficient convergence is way less. So the main difference between Gauss-Jacobi and Gauss Seidel is this term right here, where we see that once you distribute this out, you get basically the same equation for Gauss Seidel as we drew for Gauss-Jacobi, other than this last term of the negative LK, the negative Lx of k plus 1 here. What that does is basically it weights here. So when you put, here's an example. So when you put it in equation form, and then you separate it for the variables. When you plug it in for Jacobi and Gauss Seidel, you get, when you put it for the initial guess of 0, 0 for U0 and V0. When you plug it for Gauss-Jacobi, you use the V0 to get the U1, and the U0 to get the V1, and then use the V1 and the U1 to get the U2 and the V2. Now this is quite different from the Gauss Seidel method, where you have the same initial approximation here, but once you plug in V0 to get use that U1 value to get the new V1 value, reducing the number of iterations required to find a solution. So, building upon that, there's the successive overlappation method. The main difference between this and the Gauss Seidel method, which can be very easily seen in the elemental form, is this term here, the 1 minus omega, and then this term here, which is just a coefficient of omega here. So what this does is it weights the previous term to be less, and it overweights the new term, basically making it converge faster. So the omega is an arbitrary value between 0 and 2. When omega is between 1 and 2, it's the successive overlappation method. When omega is less or is between 0 and 1, then it's the successive underrelaxation method. And when it is just 1, it's just the Gauss Seidel method. So generally, SOR is about 4 times more efficient than Gauss Seidel, but that usually depends on the optimal omega value, where we can see up here the distribution for the different omega values when it comes to the number of iterations it takes. So you can see, as for this is just a specific example, but in this case, the prime Goldilocks zone was about 1.14, and that caused a fast convergence. But for general case, you would have to use the make an optimal formula here to find the root. All right, so there are some problems with the iterative method. It is less efficient for dense matrices as well as lower dimensional ones, and it doesn't converge under all conditions. So it has to fit the main rule of convergence, which is basically that the matrix of the scalar matrix here, or the coefficient matrix here, has to be less than 1 due to the error having to get smaller and smaller as you do more and more iterations. So using that same principle, and then using DLU composition and taking the norm, we can find that that equation on the right is actually equal to the equation on the left for proving convergence.
Right. So, while there are many tests for convergence for the iterative algorithms for systems of linear equations, I will be discussing two major ones. The biggest one, which is usually used, is that the system of linear equations must be strictly diagonally dominant. Now, this is a sufficient condition, meaning that if it is not diagonally dominant, the algorithm will just not work and will be completely useless. Now, the definition of a diagonally dominant system of linear equations is that the diagonal entry is greater or equal to than the sum of all other entries in that same row following the entire system of linear equations. I will show this off in a later example. Another test is called the spectral radiousness, which tests the maximum of the absolute values of the coefficient matrix. Now, these must be strictly less than 1, or the algorithm will not converge or will diverge, and the algorithm will just not work. Here's an example of a system which converges and a system that diverges. This system is diagonally dominant. As you can see, 9 is greater than 2, and 7 is greater than 3. The diagonal entries are greater than the other ones. Therefore, as you do more and more iterations, the values of x and y converge closer and closer to the exact solutions of x is equal to 1 and y is equal to 2. That iteration is very, very close to 1 and very, very close to 2. Here is an example of the output of the Python code, which we will display later. And as you can see, in the 10th iteration, we get very, very, very close to the exact solution. Now, this is an example of a system which will diverge, and the algorithm will not work on. It is not strictly diagonally dominant, therefore the algorithm will not work. The 10th iteration has values which are much, much larger than the exact solutions. Therefore, they're not the solutions. Here's the example of the code, and as you can see, the values get larger and larger the more iterations you go with because it diverges. Now, a cool way to work around this problem of a strictly diagonally dominant matrix is that you can use row operations in order to put the matrix in a format which is useful. Now, for this matrix specifically, since it is not diagonally dominant, you can actually use a row swap by swapping row 2 with row 1 in order to put 7 in the main diagonal entry and 5 in the other main diagonal entry, thereby making it strictly diagonally dominant, and the algorithm will in fact converge. Now, when should you use iterative methods, right? They are rather unreliable when it is not diagonally dominant, but they are very, very good in two specific situations. They are fantastic when a matrix is sparse, because by definition, the algorithm is built upon the fact that variables can be put in terms of other variables. So when some entries are 0, which is the definition of a sparse matrix is a matrix whose entries are mostly zeros aside from the diagonal, the equation for the other variables will have mostly zeros, thereby requiring much less arithmetic and much less computation on the person or computer who's doing it, therefore improving efficiency. It is also very good when the problem is similar to a previous problem that you've done. For instance, in fields of science where things change very rapidly and the variables in a matrix change even slightly, you will be able to plug in the previous solution for your previous equation as the initial guess for your current equation in order to use less iterations, because the closer your initial guess is to the exact solution, the faster the algorithm will converge. Now, in computer science, the name of the game is memory efficiency. And iterative methods do that absolutely amazingly, because you only need to allocate as much memory as the amount of variables which you are trying to store. I mean, think about it. The variables can be put in terms of other variables. Therefore, the next iteration of the algorithm can replace the current iteration as in its place of memory. Now, Gauss-Jacobi also has a computation efficiency which is substantially lower than its direct counterpart, Gaussian elimination. Therefore, the larger the matrix, the better it is going to do compared to the direct method. It is also, I just stated this, it is also much, much easier to implement, as I will show in the next slide with the example of our code. It is also super useful in machine learning, optimizing problems, Poisson equation, fluid dynamics, everything with many variables that are always changing, because it can represent so many things and it can solve the algorithm so much quicker for larger matrices. Here's the example of our code. As you can see, it's incredibly easy to implement. Here is the example of our code that we ran for a system that is composed of a 2x2 coefficient matrix and a 2x1 solution matrix. As you see, it converges because it's diagonally dominant, and the same thing goes for the 3x3 matrix. Here is our sources, and we'd also like to say special thanks to our advisor and professor, Mike Benami in the back, as well as the Texas Undergraduate Mathematics Conference, along with the MAA, and additionally, the Stephen F. Foster University for allowing us to use its facilities for the presentation. Thank you very much.